So, yeah, fine.
Suppose if there's some problem with the mic that you said something where I couldn't not able to hear you. Yeah, since we have got time, everyone please check the mics and everything. So is not able to hear it. Try to play with your yes, where you plug it in. Yeah. No. Is anyone else able to hear something?
No, sir.
Okay.
Hello.
Yes, Karan, can you hear you? Karan, please switch on your camera. Also, hi, Aman. Please switch on
Sir,
your
I'm audible
camera.
now? Hi, sir.
Yes. Hello. Yes, Satyajit. I thought I heard.
Sir, I'm audible now?
Yeah. Great.
Okay, thank you.
Hello, Siddharth sir, are we audible?
Yes, you are. Okay, everyone is ready. Aman, are you here with us? I think you are the last one.
Yes, sir.
Okay, Aman, I would also like you to switch on your camera.
Am I visible now, sir?
Yes, great. Okay, everyone is here. Cool. Let's start our final round of IC design competition. Yeah. So I'm sure you're all excited. You're the finalists out of the 300 registrations that we got, and then we had lots of submissions that we narrowed down to the top 6 that we are right now here and with us. And each one of you has done great work. I've seen all of your reports, very nicely done. And when I was giving you marks and when I got the top 6 with the expert, and I saw that each one of you was just 1 or 2 marks away from each other. So that's why this kind of presentation competition is necessary. And it is also just good for your experience as well. So we'll start with that. I'll give you my introduction and I'll introduce you to our judge of today. So myself, Siddesh, I'll be your host for today, and I've working with the taking groups, and I have a background in the cataloging as well as CNC machining industry. So that's my background. And today we have with us a special guest, a judge, which will be grading you, according to your presentations. We have Mr. Vivek Patil. So Vivek is working currently in Tata Autocoms and is working as a senior design engineer and has worked on basically VIW, closovers and all those things, designing all those things, as well as a few other things like the exhaust system. So has lots of years of experience. So I pass it down to Mr. Vivek now. Vivek, if you could give an introduction and speak a few words about this. Hello. Yes, Vivek.
Audible?
Yes.
Good evening, sir.
Hello, everybody. Yes, I already Siddesh introduced me very well. So there is without wasting a time in the introduction, we'll move to our main target. Okay, so let's start first all the things, and after that, I'll try to explain you any kind of relevance or any kind of things you needed. Okay.
Yes. We'll start with each one of us. So, each one of you. So we'll go by the rank systems, and I think you all know the rules of the competition, right? Each one of you will have roughly around 5 minutes. We won't have any kind of bells after the 5 minutes, but just make sure you complete it around 5 minutes and don't extend it further on. And then we'll have a Q&A session with the judge. And if the judge has any questions, they will ask you. So I think let's go. Okay, so first was Ayush Gupta. So Ayush, are you with us?
Yes, sir. Good evening, sir.
Okay, yeah. Okay, guys, I think we can start with Ayush. So yeah, over to you, Ayush. Take your time.
Yes, sir. Can I present my screen, sir?
Yes. Yes, please. Yeah, the settings
I hope my screen is visible, sir.
yes.
Yes, it is visible.
So, good evening, everyone. My name is Ayush Gupta, and I am from Vellore Institute of Technology and currently pursuing BTech in Mechanical with specialization in Automotive Engineering from VIT. And I'm also pursuing Electric Vehicle Program from Elite Techno Groups. So, for today's session, we are talking about disc brake assembly. So, the disc brake design of the Pulsar 125. So, for that, we did some calculations first. So to get the rotor diameter and what RPM will go, the disc can sustain and everything. So we did, and we come up with the 240 mm of the disc rotor diameter. And while designing it, yes. So as you can see, this is the final output of the disc rotor design. So why everything is like has some meaning in this design. So after some simulations is ANSYS 19.2, I've designed this assembly. So this is the outer part, the gray part will be where the calipers will be acting on the disc brake, and this is the inner casing where the wheel is going to attach, and this is just for the heat dissipation and providing more strength. And the material selection also for this part has done differently. This is like the outer casing will be the gray cast iron only, as because of the some economic point of view also, and having great strength and Young's modulus. And this inner part, as this is needed for this heat dissipation and providing some strength, so this we are using it for a ceramic, aluminum ceramic. Okay, and this inner part will be of cast steel or aluminum steel, whatever we can use. And these rivets, like these rivets have some meaning also. So we use them to provide some great strength to the rotor while it's going extreme stress strain analysis, and these provide a huge support during this. So I can present this. Can you see my answer screen, sir?
Yes, yes.
Okay. So while doing this, so first I've coupled 3 types of analysis together. This is like a first thermal analysis. After that, we come to the structural analysis, like how the body is going to react while the loads will be acting. And finally will be the topology optimization. So how is going to, like, what materials can be removed and how can it be made as convenient as possible. So first comes to the temperature design. So here's the a temperature variation for designing this. As you can see, for many other designs, you can see the red part is mostly coming to near to the grooves where the wheel is going to attach. So that makes the wheel assembly also a bit in danger. So we are putting these layers, so the heat dissipation is very good, and the heat is dissipated within this region only, and it's not coming to the last. And next we can see the total deformation. So as you can see, these are the maximum deformation it can sustain after giving 1 megapascal of stress pressure on these plates due to the calipers. And yes, after that comes to the topology density. So this is the these materials can be removed. So as you can see, I've already removed the maximum material that is possible here. So the most optimum design I've given for this under certain conditions is this one. So I hope that's clear. And regarding the mass and everything, so the mass of the disc rotor is varying around 600 to 700 grams. As the ceramic is very light, so it's taking very less mass. And for cast iron, it's a little bit high. And here you can see the positives and negatives of every material. So that's it for my side. And we can use different materials and optimize them as per our choice and our convenient, because we need to take the cost factor also into consideration. And that's it. Thank you very much.
Okay. Thank you, Harish.
Thank you, Harish.
Yes, so Harish, one question from me. You did some, analysis, and you took some, units for that, like you said, 1 Pascal or 1 megapascal. So for this, what kind of research you had to do? Did you do any kind of research? Where did you find this?
Sir, yeah. So I've gone through some research papers previously. So after that, I got to know like at particular rotational velocity of 50 radian per second, say 50 to 100 radian per second, and around 500 Newton meter of torque. So you
Okay.
need this much pressure will be applied, and yeah.
Okay. Yes, Vivek, sir, if you have any questions.
Yes, hello. Am I audible?
Yes, sir. Yes, sir.
Yeah. Aish, from my end, you have done that analysis and all the things. Is it done by yourself only, or you are taking the help of other?
No, sir. The analysis is done on by myself only. So I've taken some reference from some research papers and everything. That's it.
Okay. Then you just wanted some data, like you have already done the calculation and all the things, but while doing the analysis that time, you required some specific like terms which we have to be considered as a designer. Have you
Yes, yes.
considered that?
Yes, sir. So while doing the analysis itself, so we have gone through some terms like we need moment, we need rotational velocity, where the
Yes.
pressure will be
Yes.
acting. So
Okay.
everything is
And
presented in the answer. So like I've taken all the stresses and everything.
okay. Okay. Is there any kind of speed mention over there? Around
Yes, sir.
what
Around
kind of
50 to yes, sir. Around 50 to 100 radians per second rotational velocity.
okay. Okay. Perfect. No issue. Okay, from my side, Siddhesh. We'll move to the next.
Thank you, sir.
Thank you.
Okay. Yeah. Thank you, Arish. Thanks for the presentation. We move on to the next participant. Okay, and there's Tushar. Okay.
Yes, sir.
Yeah. Are you ready?
Yes, sir.
Okay. Let's go. Take your time.
I hope my screen is visible.
Yes.
Yeah. So, hi everyone. Good evening. My name is Tushar Sharma, and I'm currently a fourth-year mechanical engineering student at Quantum University, Roorkee, Uttarakhand. And without further delays, let's get straight to the problem statement. So, the problem statement for the IS-22 engineering design challenge was to design a disc brake for the Bajaj Pulsar 125 model, and to find the features like rotor diameter, thickness, material selections, and all. So these are the process parameters what all you are seeing on your screen, which will be required for the design calculations. So let's get into a quick recap of how a disc brake works. Basically, it works on the Pascal's law, which states that pressure change at any point in a confined liquid or fluid is transmitted equally in all the directions. provided the liquid should be incompressible, right? So this is a short animation. You can see that here what happens when you press the brake lever, the small piston pushes the brake fluid, right, and the fluid transmits the pressure at the brake caliper. So this pressure is same at the hand lever and on the caliper also, but the force is multiplied several times due to the area factors, right, ratio of area factors. And basically what we do every time in braking systems, we use the concept of friction to stop the vehicle. So we know that vehicle is moving at, it will have some kinetic energy, so that kinetic energy should be converted in some form using friction so that our vehicles comes into rest. So basically I will highlight 3 important points that a braking system should fulfill. The brakes must be strong enough, efficient enough to stop any vehicle within minimum distance during an emergency. There should be no occurrence of any accidents. Brakes must not wear out. The wear resistance of the brakes should be very good, and their effectiveness should not decrease with time. And it should also provide good control over the vehicle during emergency braking, right? So the vehicle must not skid. You might have heard that the conventional drum brakes used to skid a lot. So this is not happening now when we are using the disc brakes. So this is the basically a disc brake diagram, and this is the piston where the fluid pressure exerts on the brake pads. These brake pads exerts some pressure on the rotating disc, and within a few seconds it makes the disc come to rest. So using the process parameters, we have done some calculations like the relative center of gravity, dynamic load in front, and using these relations like this W x mu h by b. These all relations we have studied in our second year in the dynamics of machine. These all simple relations we are using here. So let's move on to the main points, the deceleration of the bike, right? So the deceleration means the negative acceleration which is used to stop the vehicle, right? So we have calculated it to be 6.86 meter per second square. Now the total braking force, considering the mass of the bike as well as the driver. I have taken the mass of the bike as 142 kilograms and driver weight is 60 kilograms. So the mass comes out to be 202 kilograms. So simply the braking force will be opposite to the traction forces, and simply it will be Newton's third law, mass into Newton's second law, sorry, mass into acceleration. So the total braking force comes 1385.72 newtons. So this braking force is divided on the front wheels as well as the rear wheels. So how it is divided? It is divided by means of friction. We know all of we know that friction force is mu into r. So braking force value is 1076.075 on front and it is less on rear. And why is this so? This is so because due to the momentum transfer, the more load acts on the front part of the vehicle, right? So let's move on to the torque. One thing I want to clear here that in the Bajaj Pulsar 125 models, we never see the disc brakes on the rear side. So we are considering only the front wheel for the design calculations. So the torque on the front wheel is the force into perpendicular distance from the axis of rotation, which is basically the radius of the wheel. The torque comes out to be 232.43 Newton meter. Now using these process parameters, we calculate the pressure on the master cylinder. We know that this pressure would be used in the analysis part. And force on caliper we also calculated. Now this is the main point where we have done some iterations. Like I have assumed the outer diameters and inner diameters. Like sometimes I assume 240 mm, 250 mm, inner diameter to be 150, 140. So during iterations, I found these values for the perfect design. So the torque, after assuming these design uh, diameters, is coming to be 324.326 Newton meter. So this is clearly greater than the torque on the front wheel. That means our design is correct, that our vehicle will stop. Obviously, the torque required would be more than the actual torque to stop the vehicle, right? And usually the thickness of the two-wheeler disc brake rotors varies from 3 to 4.5 mm. So I have just taken thicknesses 4 mm for our design, but it should be kept in mind that thickness should not fall below 3 mm, right? And I will first jump onto the material selection slide, then I will explain the previous slide. So these four materials basically I have taken into consideration and completed along them. This aluminum alloy is having the most suitable properties to be used for our design, but due to some limitations, it can't be used as a aluminum. You know all that aluminum has a very low melting point. So the temperature, at high temperatures, the surface of aluminum can melt. Also, it has high coefficient of thermal expansion, so it can easily deform under thermal stresses. Aluminum is also extremely malleable, and brake calipers, while applying force on the aluminum, can easily extrude it, right? And carbon ceramic alloys also have great properties, but due to these disadvantages, like it shows brittle nature and high coefficient of thermal expansion, and it is very costly. Basically, this carbon ceramic alloys is used in Formula Racing 1 cars. So due to the economic factor, we have not taken aluminum and carbon ceramic alloys both. They are kicked out from the list. So now comes on to the gray cast iron and stainless steel. These are all the just variants, G3000 and PH. We can use any variant of steel and gray cast iron. So gray cast iron and steel both are very good materials, very favorable for the design of the disc brake. But due to certain disadvantages of gray cast iron, like it shows poor strength in impact and shock loads. It has poor machinability and it is prone to rusting, simply. So we don't want our disc brake to rust in contact with air and moisture. So we have taken stainless steel for our design to be uh, for our real life applications because of these following reasons. As we know that steel is a very good corrosion resistance. It offers very good corrosion resistance under any conditions. Our bike has to run under any conditions also. It has a very high impact resistance and high strength. This, and it has a long fatigue life, means like after some time the deformation we can observe is minimum to minimum, and it has a very aesthetic look. It is easy to manufacture, and at low temperatures the martensitic alloy transforms into martensite, which is basically a steel crystalline structure that is hard. This martensite form of steel is obtained under when we study the carbon equilibrium diagram. So in our design, we have taken stainless steel as the best among the four materials. Now I come to the heat transfer calculations. See, basically,
Yeah, Tushar, let's just come to the design part now.
okay, sir. So my design is of generally design of the disc rotor is made in three types: drilled type, slotted type, and drilled and slotted type. So I have preferred drilled and slotted type because addition of holes significantly increases coefficient of friction, and also the heat dissipation also increases. So, and addition of slots also increases surface area and allows the gases to escape through the slots. And this is the main disc where the brake calipers would apply pressure. This is modeled in SolidWorks 2022. This is the constraint sketches of the holes. Then after circular patterning, we have drawn this slot, again circular patterning. This is the design of hub. I have kept the design to be simple, and this is the final design, right? We have the hub and we have 6 mounting holes. And I have made the drawing of this design. Like if anyone wants to model this rotor, he or she can simply go through this drawing. we can here note that this drawing is not intended for manufacturing, as for manufacturing it should have some GD&T also, geometric dimensioning and tolerances. And these are the renderings which are performed in SolidWorks Visualize. Yeah. Now coming to the analysis part, basically it is subjected to, our disk rotor is subjected to two main loads, the thermal and the structural loads. The static and thermal analysis of this disk brake is, disk rotor is performed in ANSYS workbench. So pre-processing steps all are same, stainless steel material is applied and meshing is done. I have my in my ANSYS workbench I have some limits of my solver, so the meshing is not so much fine. So these are the boundary conditions, the fixed support on the 6 mounting faces, pressure which we have calculated earlier, the master cylinder pressure, and the moment we calculated earlier also. Applying these boundary conditions, we can see the total deformation, which is very less, 0.006 millimeters, and the maximum principal stress is 32.326. Now this 32.326 principal stress is clearly very less than the yield strength of the steel, so the design is safe. So this and after doing this, the thermal analysis we perform, and these are the boundary conditions. This is the maximum temperature, like for worst case scenarios, how can the temperature can reach this, and this is the film coefficient for convection, and ambient temperature is 295.15. These are the boundary conditions we apply, and the maximum temperature here again is 452.43. There is a very slight increase in maximum temperature, and minimum is 435.65, which is safe for design. And these are the variations of minimum and maximum heat rates. So that's all from my side. If anyone has any questions regarding this slide, feel free to ask me.
Okay, thank you, Tushar.
Yes.
Yeah. Honestly, no question from my side. The dates are saying
Hi, Tushar.
Yes, sir.
Am I right? Yeah. I would like to say that your communication is too good.
Yes, sir.
How you are explaining the things is too best.
Yes, yes.
So, but I feel like you are doing that calculation and all the things to considering the current market conditions. Am I right?
Yes, sir. Like I'm just simply little bit modifying the design, not so much.
Okay. Okay, no issue.
Yeah.
That's it from my end. There is no question from my end also.
Thank you, sir.
Okay, now thanks, Tushar, for the presentation. Now to the next person. Okay, the next participant is Satyajit.
Yes, sir. I'm audible.
Yeah. Yes, Satyajit, you're audible.
Okay.
Are you ready?
I should present my screens.
Okay. Cool.
Sir, is it visible?
Yes.
Yes, yes.
Okay. So myself Satyajit Sagar Ekande, and good evening all of you. Now as we all know the problem statement, we should go further. Some specifications and assumptions are made before the designing, as some specifications are given in the problem statement, and some assumptions are made like the wheel diameter is taken as a rim diameter plus tire diameter, that is 17 inch plus 5 inch, that is 22 inch, and the outer diameter of rotor is taken as 210 mm. It is calculated by trial and error method in the Excel sheet. Now, as we all know, the two-wheeler braking system has two types, disc brake and drum brake. The drum brakes are not able to fulfill the requirements, like brake must be strong enough to stop the vehicle in minimum distance, and it should be efficient, must have low maintenance, and the brake must be good enough to control the vehicle. These requirements are not fulfilled by the drum brakes. That's why we come to the disc brakes. The disc brakes mainly consist of the brake lever, the master cylinder, the brake hose, and the brake caliper and the disc. As we all know the working of this brake, we should go further. Here we have made some design assumptions that the Bajaj Pulsar, the speed of Bajaj Pulsar, the braking distance, we have made the assumption like the highest speed of Bajaj Pulsar, that is 112 km/h. According to the chart given below here, the vehicle must stop within 96 meters, that is the stopping distance, and the vehicle weight we have considered is the gross vehicle weight, means the curved vehicle weight plus the vehicle weight of driver, that is 142 kg curve weight, and weight of the driver is 70 kg, that is 212 kg. Now for the calculations, we have done calculations on the Excel sheet. So the required braking force is 1724 Newton, and the required torque we can see is about 500 Newton meter. So this data is some data is given by the problem itself, that is the thrust applied by the driver, the brake lever ratio, and the diameter of tandem master cylinder piston and caliper piston is given by the problem statement itself. Now further we have calculated the total frictional force on the area, the pressure on the system, and after that the torque produced on the disc. Here we can see the torque produced on the disc is 530 Newton meter, and the required was 481. So it is good for the design. After that, the deacceleration comes 8.97 meter per second square. By using the kinematic equations, we can see the stopping time is 3.47 seconds. Assuming the time required for thinking and pressing the brake pedal, we are assuming the time required for thinking and brake pedal is 0.54 seconds. So for getting the stopping distance, we are again used the kinematic equations. Then we have got the stopping distance as 53.99 meter, that is 54 meter. Here we can see a tabulated part, which is the stopping distance for specific speed, that is for 112 it is 45 meter, for 100 it is 43. It is given in the tabular structure. For thermal consideration, we have done some calculations for getting the heat flux. We are here, that is 11,24,531 Weber per meter square. It is used for the analysis. Now it is the fully constrained sketch. There are totally 16 holes for the heat dissipation or convection, we can say, and 6 slots for the same. And these are the analysis reports. We can see the minimum factor of safety come is a 2. That is the minimum factor of safety, and the total maximum deformation is 0.011 mm. Then the thermal analysis done. The heat flux given is we calculated, that is 1.2 Weber, 1.2 lakh Weber per meter square, and the maximum temperature according to the ANSYS is 217 degrees Celsius. Now this is the actual sketch or actual image of the disc brake. I have kept it simple for easy machining and all. And these are the some views of the model, like front view, side view, and the isometric view. This is the isometric render of the model. I have used the material stainless steel 410 because it gives very good properties, as it is very high corrosion resistance. It is having a very high tensile strength, required for our design, and it is cheaper if compared with the others. It is low in weight, we can see. As the energy of motion is converted into heat, it should be dissipated. So the dissipation is achieved through 3.7 mm thick disc brake. Due to good structural and thermal properties, the stainless steel 410 is chosen. As we can see the speed versus stopping distance chart, we can see for 112 it is 54. We have seen it before. Now, considering the maximum speed of Bajaj Pulsar 125, it is 112 km/h. It is the worst condition that the specific bike brake disc can go through. If we apply rear brakes and front brakes simultaneously, the stopping distance and stopping time will be reduced more, and this will not result in any bad condition. The design and calculation are done for the mass reduction and optimization. As the original disc diameter is 240 mm, we have made it to 210 mm, and the weight of our design is 525.03 grams. It is low in weight, and the assumed stopping distance is 85 meter, and the actual stopping distance is 54.03 meter. It is safe. After studying the analysis and calculations, we can say that the design can sustain for the conditions given, that are the worst conditions, like the highest speed of the vehicle Bajaj Pulsar 125. Okay, this is from my side.
Okay, thank you, Satyajit, for your presentation. One question from my side. When you said you consider the stainless steelless material, so what other materials did you consider and did you compare it with?
Actually, I didn't compare with the other materials because I have used the material in my real life situation. I have worked in the Supra and go-karting. I have used the same material there. That's why I directly go through the stainless steel 410.
Oh,
Is there any other questions?
yes, Vivek sir, do you have any question?
Yeah, Satyajit,
Yes, sir.
you mentioned assume stopping distance is 85 meter.
Yes,
Am I
sir.
right? And you mentioned there the actual stopping distance is 54. Is that only done with what kind of the parameters?
Actually, sir, I can show you here. There is a chart showing the typical stopping distances for the speed. I'm not sure that you are able to see. There is a link given below, but it is showing for the 112 km/h speed, the stopping distance should be 96 meters.
Okay.
Okay, this is the assumed, but as we all know the road conditions and traffic conditions in India, we have considered it as 85 meter.
Okay.
And the calculated stopping distance is 54 meter.
Okay. And for the calculation, what kind of factor you have considered, as you know, like road conditions and all the things? Then how you assume like
for the
54
road
is-
conditions, I haven't used any factors, but I have decreased the stopping distance. As I have mentioned earlier, it is 96 meter by the chart. I have taken it as 85 meter.
Okay. Show me
And-
that calculations if you have.
Okay. Just a minute, please.
Okay.
These are the calculations for the stopping time and stopping distance. The kinematic equations is used. By using the kinematic equations, the stopping time is 3.47 seconds.
Okay.
And we are assuming the time required for thinking and pressing the brake pedal as 0.54 seconds.
Okay.
Then the total time becomes 4 seconds. And after that, for the stopping distance, the another kinematic equation is used. From that, we have got the stopping distance as 53.99 meter, that is 54 meters.
Okay. Got it.
For the
No issue.
speed 112, which is the highest speed I have considered.
Okay. Perfect. No issue.
Okay,
Yeah, that's
thank
it from my end.
you. Okay.
Thank you.
Okay, thank you, Satyajit, for the presentation. Now, our next participant.
Thank you.
Okay, next participant is Madhav. Okay, Karan, you're with Madhav.
Yes, sir.
Are you guys ready?
Yes, sir.
Okay.
Are we audible?
Yes, you are.
Okay, so myself, Madhav Makana from Eddie Patel Institute of Technology, Gujarat.
I am Karan Darji, third year automobile from AD Patel Institute of Technology, Anand, Gujarat.
So let us jump into our presentation. We have got the same problem statement for designing of disc brake rotor, finding the rotor diameter, thickness, and material selection. So initial 2 days we have gone through. Just a second, I forgot to present myself.
Yes.
Sorry for the details. Is it visible, sir? Hello.
Yeah.
Yes, it is visible.
Okay.
Please go ahead.
So initial 2 days of our designing phase, we have gone through a research phase. We have analyzed many disc brakes of bikes in our colleges. In our college, we have also analyzed the disc brake of Royal Enfield also. And after that, we started with the data given to us. And as a designer, I found that the top-bottom design works for most of the cases. So we started with the pedal ratio and found the forces acting on the cylinder of caliper. Then we found that the pressures and everything. And these are the calculations we done. One thing we have assumed over here for the calculation is the brake pad area. For that, we have assumed that the brake pad outer diameter is equals to the outer diameter of the brake rotor, which we have assumed to be 200 mm, which we found as a design of a Pulsar 125. It's good to keep a lower outer diameter, which will reduce the weight of the rotor, and also economically it will be. Then after that, we have done all the brake pad calculations. And from that, we have found that the frictional force, keeping in mind the constant wear theory. And from that, we have found that the braking torque and effective radius of braking force also, which was 88 m. Then area of brake pad which we have assumed is, we have written over here. And on researching, we have found that Bajaj Pulsar is using 190/17 tire size, from which we founded the overall size of the tire, from which we founded the overall diameter, and we have assumed that the top speed of as Tushar told, it's 112 kilometer, from which we got the top angular velocity as 136 radian per second. And taking into consideration the mass of the vehicle plus the rider's mass, the force of deceleration we got is 2138 Newton. And deceleration from Newton's second law we have found to be 9 meter per second square. And considering initial velocity to be equals to 60 kilometers per hour, we found that the brake distance to be 14.4 meter. Now, as a designer, it's a very hit and trial whenever we design anything. So what we have done is, we have done all this calculation in MATLAB. So this is our MATLAB program. So whenever we used to change any
I think the laptop is interesting.
I think is there any network issue?
Yeah, I think. We'll wait for them. Tell them next two participants be ready. That is Caliper, and then finally we have.
hello.
Yes, Karan. Yes.
Yes, Karan.
Hello. Yes, sir.
Yes, you're on.
Yeah, yes, Karan. Please.
Continue.
Okay. So we increased the number of holes and we provided a small slots, not a longer slots, but a small slots, which will be easy for manufacturing. And this way the surface area is increased a lot and it will help in a heat
You
dissipation.
have shared your screen?
Yes, sir.
Screen is not visible to me.
It just,
Is this visible to Siddesh, you?
Okay.
Yeah.
No.
Now it's.
Done, sir?
is it now visible?
Yes. Yeah. Please, go ahead.
Okay, so we provided these slots. So this increased the surface area and which will help in heat dissipation. Also, what one thing we observed is that in current Bajaj Pulsar, there is no peripheral design provided. One thing reason is that to make it economical, but to increase the heat dissipation a little bit more, we have also provided a peripheral design. And we have also provided a chamfering at the edges on outer edges, which will further increase the surface area. And these are the render images we have done. The material we have used, we have analyzed three materials. One was grey cast iron, stainless steel, and aluminum. Out of this, aluminum was having a best thermal properties, but considering the cost and other mechanical properties, we have gone with grey cast iron. And these are the properties which other participants has mentioned. And analyzing those, we have gone with grey cast iron itself. For analysis, I want to share over here. We have done static structural analysis, which we have already submitted in the first phase. We have provided a load over here in the brake pad area. These are the meshing we have created. It was a default mesh, but we have decreased the element size to capture the curvatures and holes properly. And we have provided rotational velocity. And then we have provided the force, which we have calculated through MATLAB and all things, from which we have got the results. These are the forces we are applying. These are the fixed supports provided at the mounting holes. So is my screen visible?
Yes.
Okay.
Yes.
And afterwards, we have got these results. This was total deformation. At the brake, we can see it is 0.01 mm of deformation was there. Further, we have equivalent von Mises stresses, which is way beyond the yield strength of this. And we have stress, shear stress also. Then we have also done combined thermal and structural analysis by providing a temperature at the brake pad locations. So these are the results. We have temperatures provided at the peripheral location. This is the red colored mark are the where temperature was provided of 100 degrees Celsius. And these are the results which we got. This is the temperature distribution. And this is the heat flux. We can see over here from the chamfering which we have provided, from there the heat dissipation is getting a lot. So it has marked an improvement in the design. And this is the total deformation which we are getting. What one thing we have improved our submitted is this transient structural analysis. What one thing we have found is that whatever analysis which we have seen in YouTube or in research paper is that they are keeping the forces on whole brake pad area and not on the just brake pad. And temperature also they are providing on the whole surface area of the on outer periphery. What I think is this is a illogical thing. What should be done is we are providing force to the brake pad. Brake pad is compressing the brake. From that heat is generating, and then that heat is providing the stresses, thermal stresses. So apart from static structural analysis, we get into the transient structural analysis, which provided a better result also. So this is the transient structural analysis we did. We have two brake pads over here. This brake pad design we have calculated, which we saw in MATLAB. What we did in this is we provided over here, we can see, we provided a frictional contact between this disc and this brake pad over here. And the frictional coefficient we are already provided, it was 0.42. On both the sides, we have done this on both the brake pads. And we have also provided rotational velocity. This is the meshing which we have done. We have here also decreased the element size to 5 mm from default 14 mm to better capture the curvatures. And this is the rotation we have provided to the mounting holes. This whole disc is there. And these are the results which we are getting. This is the total deformation. Over here, we are not getting the radial deformation. It was just a total deformation. I will work on it to find the better solutions. This is what I want to emphasize on. This is the equivalent stresses which we are getting on a real situation. From this mounting hole, the stresses are getting divergent. And these are the equivalent stresses. And this is the elastic strain which we are getting. And this is the frictional stress which we are getting. And the last thing which I want to show over here is this video which we have captured from the NCs. So this way the stresses are developing in the disc rotor, we can see over here. And without brake pad. So without brake pad, we can see how the stresses are, when disc is rotating and we are applying the brakes, how these stresses are getting all over the disc. So this was from our side. Thank you very much.
Thank you.
And
Okay, thank you,
just
Madhav and Karan.
in conclusion, what we found is that from our design, 200 mm was the outer diameter with 4 mm of thickness. And from this, we are getting a braking distance of 14.42 at 60 km/h.
Okay,
Thank
good.
you.
Thank you, sir.
Thanks for the presentation.
Okay.
So
Thanks, Dr.
one-
Nice.
One question from my side for you guys. Yeah, one thing is I would have liked to hear a few words from Karan also. So yeah, that's just one comment from mine. One question is, what is the thickness that you have considered for this test?
Disc rotor thickness, we have put 4 mm.
4 mm. Okay,
Okay.
and any kind of assumptions based for that, or any kind of reasoning behind that?
Reasoning is that mostly we have found that 4 mm thickness is everywhere it is used in every bike, not only in Bajaj Pulsar. Most of the companies are using 4 mm and minimum thickness is mentioned to be 3.5 mm.
Okay.
So in our initial 2 days of research, we have done this and we were analyzing all the bikes with this loops.
Okay.
And so it's better to use the already designed materials.
Okay, good. Yes, on to you, Vivek sir, if you have any doubts.
Yes, Karan, the presentation is very good. Actually, you've taken a lot of
Thank you, sir.
efforts for the analysis and all the things. And just one thing, I just wanted to know that have you consider any kind of coefficient of friction over there? Because of
Yes.
every braking condition, we have to be consider the coefficient of friction.
Yes, sir, it was provided to us in the booklet only. It was 0.42 between the disc brake and brake pad, rotor and brake.
0.42.
It was provided to us.
Okay, perfect. No issue. Thank you very much. That's it from me.
Thank you.
Thank you, sir.
Welcome.
Okay, thanks again, guys. Next we have Chanakya.
Yes, sir. Am I audible?
Yes, you are audible, Chanakya. Are you ready?
Yes, sir. Yes, sir.
Okay, go ahead.
Yes, sir. A very warm good evening to respected panel and my dear friends. Myself, Chanakya Dhiras, pursuing third year mechanical from NIT Kurukshetra. I am here along with my friend and teammate Pritham, and I would like to present our presentation. First thing, when we look into the disc, the main properties of the disc should be like good compressive strength, good high strength even at elevated temperatures, high thermal conductivity, excellent aberration resistance, and high stiffness and the less weight. And coming to the problem statement, here we have to find the rotor diameter, thickness, and the material and design. Here there were some specifications given in the project like pedal ratio, wheelbase, center of gravity, distance between center of gravity and rear wheel, coefficient of friction. And from the general scenario of the pulsar, the weight of the bike is around 140 kgs, and assuming the driver weight to be 60 kgs and the weight of the whole vehicle be 200 kgs. And when coming to the calculations, while calculating the torque capacity, there are mainly two theories. One, uniform pressure theory, and the other is uniform weight theory. In the uniform pressure theory, the pressure is uniform all over the disc. This is only valid for new brakes. It cannot be used for old brakes. Here the pressure is the maximum pressure applied, which is a constant. As it is can be used only for new brakes, we go with uniform weight theory. Which can be used for old brakes. Sir, am I audible?
Yes, keep going.
Yes, yes, yes.
Power loss. In which power times R is a constant. Now the calculations will be said by my teammate Preet.
Good afternoon, panelists and my dear friends. As mentioned by my teammate Chanakya, I'm Preetham of pre-final year mechanical from National Institute of Technology, Kurukshetra, and I'm going to explain to you the calculations and the solid modeling part of this project. Now, the calculations have been conducted in software called MATLAB, which is very good for scientific and engineering calculations. As discussed in the PPT, the whole calculations part has been divided into 4 steps, and I'm going to explain to you each step. In the first step, it can be seen that we have defined all the input parameters according to the problem statement, and the required torque and required torque in both front and rear wheel have been found using concepts like load transfers and friction. Now coming to the step 2, we have considered the brake assembly in which we have taken all the values as given in the problem statement, and we have calculated the force which is being applied on the disc brake. Now what we have actually done to calculate the internal diameter and the outer diameter was we have considered it to be a range. Like we have taken the outer diameter as a range and input diameter as a range, so as to provide a visualization which will help us in deciding which point to go for. As can be seen from the figure.
I think they have a network issue. We'll wait for them. Also, for everyone else, I'd like you guys to know there's lots of people on YouTube currently cheering for you guys. So yeah, you have good supporters behind you.
Okay, am I audible?
Yes, yes.
Okay,
Yes,
sorry.
Preetham.
Yeah.
Continue.
Okay, now we have chosen a point where the curved surface is crossing the planar surface because we need to cross the required amount of torque for the braking to be successful. So as can be seen from the 3D graph or the surface graph, we have chosen it to be this point. Now in
Preetham,
this
make
point,
sure you're sharing a screen again.
okay, I'm sorry. Just a sec. Yeah, is it visible now?
Yes.
Okay, thank you. Okay. Now this was a plot which we have made using MATLAB. We have plotted the internal diameter with the outer diameter against the torque. Now, as I've already explained, the planar surface is the required torque, and it would be a threshold or the point which we have to cross to perform braking. Now, this point has been chosen because it is just in the it has just crossed the plane, and we wanted to choose the minimum internal and outer diameter so as to reduce its weight. So now the point has been decided so that the internal diameter is 15 and the outer is 28. And this is a piece of code, and we have used another plot just for a different visualization of the brakes crossing, like the values crossing the threshold of the torque. Okay, now coming back to the PowerPoint, these were the 4 steps by which we have calculated the internal and the outer diameter of the brake. Now coming to the 3D modeling, which is conducted in SolidWorks, we have actually gone through 3 prototypes. Okay, the first prototype which we had carried didn't had a high amount of mass, which wasn't desirable. Then we have gone for an assembly type brake construction, but the problems were there was a lot of problem in heat transfer. As it was an assembly, things were connected and heat transfer wasn't efficient. So this is the final design which we went through. Now there were 3 goals. You can call it goals. Okay, there were 3 primary goals which we wanted to achieve. The first being weight reduction. So to reduce weight, we had to create these slots or holes which were nearer to the inner radius, because whatever force is being applied on the brake would be on the outer one. So we have created these slots. Now we have conducted structural analysis on this to decide the dimensions and the gaps to leave them, because the mountings would be inside and there would be a lot of centrifugal force on the brake system. And our third goal being heat transfer. To increase the heat transfer, we have provided slots which gives it more surface area for the convection of air, so that it would show good heat dissipation. Okay, now this is the design structure we went for. And one more thing which we have done was cost analysis. Actually, this cost analysis is a report which is generated by the SolidWorks suite.
Pritam? Okay, I think they are having connection issues again. No issues, we'll wait. Guys, I hope you're even learning from each other's presentation at this point, right? There's, each of your projects I've seen so far, each one has a different way to start looking at the problem and start solving it. So that's, great to see, because that is basically what design engineering is. We have lots of ways to design just one element, one component. So that's great to see. And I think each one of you can learn from the other fellow participants, how they have done it or what they have done maybe better than you think. Okay.
I'm sorry, actually, there are consecutive power losses in our
No issues, no issues.
So okay, till where was it clear? Can you give me just a report?
You're on the cost report.
Okay, cool. I'm sorry for the inconvenience, actually.
No issue.
Okay, just close this and open the presentation. Sure. Okay, coming back to the topic, as I was discussing, the cost report has been generated via the SolidWorks suite, and we actually aimed for less cost, and this is based on casting. And so okay, now like continuing the presentation, this is our front and rear view. We have given this like small slot for mounting it on the brake assembly. Now this would be our isometric view of our brake disc design, and the thickness has been decided to be 4.2. This has been done using an iterative process in ANSYS. Like the whole design, like the numeric part of the design has been done using ANSYS as using the 3 goals which I have already mentioned. Now the ANSYS reports and how it was conducted will be explained by my friend Chanakya. Hello, sir. Welcome.
Yes,
When
Chanakya.
coming-
Also,
Yes.
Chanakya, one thing, if you're having network issues, you're free to switch off your camera. So the network will ease through.
Okay, sir.
Yeah,
Thank
switch
you,
off your cameras.
Okay, sir. When coming to ANSYS, we have chosen 2 materials from the main motive is to maximize the maximum equivalent stress should be maintained, should be minimum equivalent stress should be there, weight reduction should be there, and heat transfer like convection should be also there. And then here we have performed on the 2 materials, iron cast iron analysis and stainless steel. We have performed steady state thermal, static structural on both, and we also tried it in topology optimization, but that wasn't good, so we skipped that part. And coming to the ANSYS, we have given the temperature, convection, and we have, as this is connected to the wheel, we have given the rotational velocity, and we have given the fixed support. The area of the brake pad had been projected on the brake disc, and the pressure or the force, braking force, were applied on this area, so that as the braking force will not be applied on whole the disc, so we have projected the area, and we have just applied the force on these areas, and we got the stresses when we compare the 2 results, like gray cast iron and stainless steel. By using many iterative methods, we came to this dimensions of the model. After many iterations, this model had been made. Nearly 10 to 15 iterations had been made, and the thickness was chosen accordingly. When coming to the material properties, we have compared, as I said, we have compared gray cast iron and steel. So as there is no much difference in the maximum yield strength and thermal conductivity or overall heat transfer, they both perform almost the same. And when coming to the density of the gray cast iron is less than the steel. So the weight of the model is less automatically, as the maximum stress that came from our analysis hasn't yet reached the maximum limit of yield strength. So we go with gray cast iron. So that is from our side.
Okay. Thank you, Chanakya and Preetham. So,
Thank you, sir.
no questions from my side. Vivek, sir, if you have any questions.
Actually, from my side also, there is no question. Only thing is that you mentioned in your first slide that coefficient of friction is 0.7. Is this correct or something?
Sir, this is the directly a snap taken from the problem statement that was given from the Allied Techno groups. Sir, there are like two types of
Yes,
friction. One would be the friction between the wheel and the ground, which is taken to be 0.7, and the friction which is taken between the brake pad and the brake disc was taken as 0.42.
Okay, perfect. Because as per industry standard, the friction between that brake pad and that what do you mean brake shoe, it should be not more than 0.5. It's around 4.5 we'll consider, but better like we have to be considered from 0.35 to 0.45. So that's why only I ask you. Okay.
Yes.
Apart from that, everything is okay.
We have also taken a factor of safety for the braking torque because the natural phenomena is different from what we get in the analysis.
Yes, sir. We have taken the factor of safety to be 1.1 in the braking torque calculation part.
Okay, perfect. No issue.
Thank you, sir.
Thank you, sir.
Okay, thanks again, Chanakya and Preetam, for your presentation. Now let's move on to our final participant, Aman. Are you ready?
Yes, sir.
Okay, great. Go ahead.
Is my screen visible?
Yes.
Yes. So, good evening to everyone present here. My name is Aman Sharma, and I am here to present my project report. Before I start, I would like to thank capable early techno groups and AICTE for collaborating and providing us with such interesting competition. So let's begin with the process. So the process that I used for the whole project was beginning with the problem statement, trying to know what the problem statement is trying to convey. Then moving on towards understanding the whole working, which included getting the resources from elite techno groups and knowing more about the whole braking system and the whole designing process. Then I moved on towards the calculation part, where I will be showing in the next slides, which was one of the most important parts, as it included the safety conditions and also the materials that I have considered. Then I moved on towards designing of the disc brake. Once I had got the calculations that were sufficient for having the safety conditions on, so I moved on towards designing. Then I moved towards the results part and conclusion. And at last, I moved towards report formation. So now moving on towards the problem statement, which states that do the necessary disc brake calculations to figure out the rotor diameter and thickness, material selection, and design a disc brake for Bajaj Pulsar 125. Next, we move on towards the calculations. So here in the calculations, we are asked to find the rotor diameters, which is the outer diameter and the inner diameter, and also the thickness of the brake disc. And here are all the parameters that were given to us. And also there are some values that I have assumed, which I would be explaining in my calculations. Here I've calculated the total weight, which will include the weight of the bike and also the rider, which comes out to around 222 kgs. In this slide, I have calculated the dynamic load, which is to be applied on the front and the rear wheels, which then helps us in calculating the weight distribution for the front and the rear ends. This is all these calculations are being done to find the torque that will be applied on the front wheel, which is one of the most important parameters that we need for getting the factor of the safety conditions on. So here we calculate the deceleration and the braking force on both the wheels, which in this next slide helps us in calculating the torque, which is on the front and the rear wheels. We get the torque on the front wheel as 253.33 Newton meter, which is one of the most important factors, as this is to be compared with the torque that is being generated from the brake caliper, and which should be more than the torque on the front wheel. So now we move on towards calculating the torque from the brake caliper. So for that, we need the pressure on the master cylinder, the force in the caliper, which has been calculated in this slide. So moving on, we get on towards the final calculation that we needed, which was the force by which
we get the torque, and for reaching there, we needed two parameters, which were asked for us to find. That was the outer diameter and the inner diameter. So this step here requires an iterative process. So for the iteration, I have considered the software Microsoft Excel. Inputs I have calculated from this table. As you can see, these values are the ones that I have done the iterations for. And here is the torque over here, as seen somewhere in red. It is because those torques are less, the torque value is lesser than the one for torque on the front wheel. And so we neglect those values. And the one value that I found was which was safe and was good was the one that I have highlighted in green. And having that value into the calculations, I could see that the torque on the front wheel was lesser than the torque being generated by the brake caliper, which was what we needed so as to get the safety conditions on. And one would ask why did I consider these calculations when because while I was researching, there were many more calculations that were there online, but I chose these calculations because the brake disc is used for the stopping of a bike, and these are the conditions that satisfy and make us confident in our design, as it shows that the disc that we are producing is doing the job it was assigned to do. So moving on towards the remaining calculations that I've considered are these. So these were the calculations which were for the mounting holes. So the mounting holes over here are having an PCD. So for calculating the PCD, I have considered some parameters, which were the ones that I was speaking at the start of the slide. So those are like the clearances that we need from the inner diameter towards the PCD. So based on these clearances, you can see that your whole design would be whether safe or whether it would break during more force or during more heating. So here I've calculated the PCD. And moving on towards the designing aspect. So I have selected the software called SolidWorks for designing. And this is like a whole fully constrained sketches summary type, which would help us in creating the whole model from scratch till the end product. So here the first image represents the inner and the outer diameter of the disc brake. And the second one here represents the fully constrained sketch with the mounting holes parameter. The third one here represents the whole patterning of the drilled hole that we need for heat dissipation. And I have selected drilled holes over the slotted holes, as in slotted holes, if you were to have a slotted hole system in your disc brake, it will result in easy wear of the brake pad, which we cannot afford as we are building an economical bike. And these are usually the slotted holes are usually used in high-end performance bikes, which have the brake pad of the material of ceramic or the carbon fibers, which is not the case in our Bajaj Pulsar 125. So I have gone with just drill holes. So moving on towards the drawing sketch, this is the drawing sketch that I have made in SolidWorks, which if anyone would want to create the whole model, could go on with getting these dimensions. So next we move on towards the tree structure sketch. So this is the tree sketch manager on the left hand side, which shows us all the features I have used and all the material I have selected. And the one on the right is the final model that I have created. So moving on, this is an representation of my front view and the rear view of my final model created. So hopping on towards the rendering images. So both of these images were rendered using the application PhotoView 360, which is present within SolidWorks. And now moving on towards one of the most crucial steps, that is material selection. So for material selection, I was going through various resources online, and one that was the most effective in my point of view was the ASBY chart. So the ASBY plot is created by a scientist who was known as Michael ASBY. So he created these plots based on all the material properties that are known to us, and through all the experiments that we get, like we get the coefficient of heat transfer and the density and all the other parameters being considered. He created like various plots with all the properties being considered in both x and y axis. So this is one of the examples that I had used. So as seen here, this is a plot against Young's modulus and density. So as seen in the left one, the left image shows us that the plot is for like all the materials being considered, from metals, to the natural materials available in the environment. So as you can see, the straight line present. So that line is the one where below which the materials are not to be considered, as those are not those are more dense and have less Young's modulus. So having considered those materials will not be suitable for our desired output. So we just try moving the line parallelly upwards and try eliminating all the materials that are not needed. As you can see, the one in the right, the image, it shows us after having eliminated half the materials, we are left with few materials, that is the metals and alloys. So those include the gray cast iron, aluminum alloys. So this was one of the plot that I had used. So moving on towards the materials part. So during my research phase, I found that generally the materials that are used for disc brakes are stainless steel, aluminum alloys, cast irons, the gray cast iron ones, and the cast irons with various hardening processes, and also carbon fibers. So the table 1 over here, it shows us a comparison between all these materials against their properties. So aluminum was really good for its strength and other factors, but it lagged a few parameters, like the melting point was like 500 degrees
Raman,
Celsius.
sorry to interrupt. Let's try to conclude this.
Yes, sir. So just concluding, so it was not that sufficient for us, and also it was high in cost. So we neglected the aluminum alloy. Moving on towards the carbon fibers, those two were best, but too costly, so we had to neglect those two. So the only materials left were stainless steel and gray cast iron. Stainless steel could have been selected, but it was more dense, and being more dense, it will reduce the efficiency, as power to weight ratio would be less. So I went with gray cast iron, but it was less in thermal conductivity, but that could be tackled by hardening the material. So I went with gray cast iron. So concluding my presentation, I would like to say that the outer diameter that I selected was 230 mm, the inner was 170 mm, and the thickness was 4 mm. The thickness, I took 4 mm as through my research, I got to know that the range was between 3 to 5 mm, and the 4 was the most ideal, as it was being used for most of the vehicles. And on the right is like the mass that my disc brake has, which is 593.08 grams. and the material selected is gray cast iron. And also, I would like to see that the disc brake that I have designed is more efficient and compact than the original model due to the following mentioned parameters. Thank you for your attention.
Okay, thanks, Aman. Thanks for the presentation. Honestly, no questions from my side for now. Vivek sir, do you have any questions?
No, actually, from my side also, there is no question. From like 5 to 6 seminar we're attending, and every seminar having the different things and different like ideas. So we'll all clear all the things. So from my end also, there is no question.
Thank you, sir.
Thank you.
Okay. Okay, then, hello. Yeah. Thanks everyone for presenting your presentations, your reports. Everything was really nice. I hope everyone got to learn something from each one of you. And I hope you also know that the winning ceremony, the final ceremony will be on 8 p.m. today, right? We'll have the scores finalized for you guys, and we'll get to know who's winning by 8 p.m. Before we end this session, Vivek sir, I'd like you to talk about the session that we had today. What was your view on this?
So hello everybody, welcome back. So
Hello, sir.
yes, yes. Actually, if we're like a designer, we have to know each and every things as we consider. You're considering the different materials you research for the lot of time. So for the like there is also various factors will be there to selecting proper material as well as proper design consideration. With the help of like a design is not the only thing to be draw in the like a modeling or to be draw in the any kind of software and all the things. So we have to be like think on like basis of how the part will be manufacturing, what kind of the manufacturing process will be there, how the cost we will like minimize the cost for the manufacturing, and main thing is that the performance depend upon the performance, manufacturing cost, like manufacturing factors like cost, and we have to be consider the environmental conditions also a lot of times. So depend upon that kind of all the factors, we have to be design each and every parts. So as today's session, like in the like if we think like a disc brake, that is we see it's only like a very small component, but for that also we have to be research lots. That's why only like you put it the effort on that, and you learn a lot of things, new things, I hope. So keep learning, keep growing, because of like every single moment we have to be go, and we have to be like consider the best engineers and best like designers. So thank you very much for like attending and joining the competitions. In the ETG there is a lot of competitions is ongoing every day by day, as well as like next time also. So please try to be attend all the thing, all that things. It will be boost your like confidence as well as knowledge. uh, Here is not like that we are just attending for like winning the prize and all the things, because I like today we like think now also we have to be discuss who is the winner, because everyone did in a very best manner, as well as everyone put it, their effort much more than they have like that's why it will be like very complicated for us also. But only thing is that be like keep learning, keep growing, so it will be help you for the next level to how to like speak confidently, how to explain the things, what kind of the things we have to be add in the presentation, what kind of things we have to be speak directly. So there is no like winning and losing is the part of like every time, every game. But keep learning, and thank you so much for like joining us. Thank you.
It's thanks.
Over to you, Siddesh.
Yeah, thank you, Vivek sir, for also attending and being a judge today. And thank you, everyone. We'll meet at 8 p.m. today, okay? And we'll close the session. Okay. Thanks everyone, and see you again at 8 p.m.
Thank you.
sir.
Yeah.
Thank you, sir.
Bye.
Thank you.